Okay, let's take a look at how to get started on lesson 4.3.1, the homework questions. Now, after we go through one together, it's a good idea to pause the video and see if you can do number 2 on your own, just so that then you're kind of getting the hang of it and practicing on your own. So for number 1, it says how many moles of ethanol would be required to generate 1,000 kilojoules? Well, it's a great idea to always start by writing what you know, 1,000 kilojoules. And we want to figure out moles. So is there a conversion that we know already about ethanol that tells us how much energy per mole ethanol gives off? So if we scroll up to the top, it says here that ethanol releases 1,370 kilojoules per mole. So for every 1,370 kilojoules released, that was 1 mole. So we don't even need a mole then to release 1,000 kilojoules. So we need a fraction of a mole. Multiply across the top and divide by the bottom, and we get 0.73 moles of ethanol. So go ahead and pause the video and do the same thing for number 2. Only there's one extra step. After you get it into moles, it wants you to convert it into grams. So for number 2, to check your work, 7.5 kilojoules is how much energy we want to produce from butane. So we go back up to the handy dandy table. Butane is 2,870 kilojoules per mole. So we definitely don't even need close to that because we only need 7.5 kilojoules. And we can actually stop here and calculate how many moles that is. 0.0026 moles of C4H4. I multiplied across the top and divided by the bottom. Oops, C4H10 I meant here. Okay, now if we want to know how many grams C4H10, or how many 0.0026 moles of that would weigh, we've got to multiply by the molar mass. So 1 mole of C4H10 is equal to, we've got to go to the periodic table to add this up. Carbon has a molar mass of 12.01, and there are 4 carbons. Plus, hydrogen is 1.01, and there are 10. That adds to 58.14 grams. So that's how much 6.02 times 10 to the 23rd, or 1 mole, of C4H10 molecules weighs. We only need 0.0026 of a mole. So we're going to multiply that fraction across the top, and that gives us our final answer. We would need 0.15 grams of the butane to generate that 7.5 kilojoules. Number 3. How many kilojoules of energy would be provided to a fan motor if it took 15.5 milliliters of hydrogen gas? So this is similar to the calculation that we did in this lesson. So first, it'll be helpful to convert milliliters into liters, because there was one new special conversion. 24.5 liters of gas is equal to 1 mole. So that means if you had 1 mole of hydrogen gas molecules, they would take up that volume of space. So now we can use hydrogen's value from that table at the top. 1 mole of hydrogen releases how many kilojoules of energy? 242 kilojoules. And we multiply everything on the top, divide by everything on the bottom, we get 0.153 kilojoules. So I can slash out all of my units that are canceling out here to see that, yes, indeed, we end with kilojoules. And the last one gives you some extra information. It says you've got a car burning octane. They go for 30 miles, 30 minutes, and they used 3,785 milliliters of octane. Now, it also tells us that the density of octane is 0.702 grams. So every 1 milliliter weighs that many grams. And this is C8H18. That is the formula for octane, and it's provided in the table at the top. Okay, so now that we've got grams of octane, we can divide by the molar mass to convert this into how many moles we have. So C8H18, carbon's molar mass is 12.01, hydrogen is 1.01. If we add all of those together, we get 114.26 grams. So we know 1 mole of octane produces 5,430 kilojoules, because that's what it says on this table at the very, very top. Okay. So now multiply across the top and divide by the bottom. 126,272 kilojoules is how much energy the car is using when it uses 3,785 milliliters of that octane. So the key here is canceling out your units so that you can ultimately figure out what the problem is asking you to do.